Okay, so good evening, everyone. So our topic for this is about, of course, a fundamentals of data warehousing and data mining about classifications of decision trees, Bayesian, nearest neighbor classification. Okay, so again, this topic focus more on a myriad of options exist, no, when it comes to classification. So in general, there isn't a single best option for every situation. That said, three popular classification method, as what we mentioned, is the decision trees, KNN, and naive bias. Now, can be tweaked for practicality every situation. So the naive bias and KNN are both example of supervised learning where the data comes already labeled. Now, decision trees are easy to use for a small amount of classes. So if you're trying to decide between the three, your best option is to take all three for a test drive on your data and see which produce the best result. So if you're to classification, a decision tree is probably your best starting point. So it will give you a clear visual, and it's ideal to get a grasp on what classification is actually doing. KNN comes in a close second. So although the math behind is it is a little daunting, you can still create a visual of the nearest neighbor process to understand the process. And finally, if you want to dig into naive bias, no, the math is complex, but the result is a process that's highly accurate and fast, especially when you're dealing with a big data. So I'll just want to share the video presentation of your classmate related to the said. If you have some questions related to the topic, let's you just simply put your suggestion, comments, or additional inputs in our chat box for Mr. Peña to answer all those questions. Now,
Good evening, classmates. This is Kevin Pena, reporting for the subject fundamentals of data warehousing and data mining. Um, so, yeah, let's get into it. So, for my topic for today is classification, um, decision tree classification, Bayesian classification, and the nearest neighbor classification. So first, let's get into classification. This is a technique that separates data points into different classes. It allows you to organize data sets of all sorts. Which includes complex and large data sets as well as small and simple ones. This primarily involves using algorithms that you can easily modify to improve the data quality. So basically, classification is how you classify one data from, how do you separate one data from another, or do you group them together? So for types of classification techniques, there are multiple types of classification algorithms, each with its unique functionality and applications. All of those algorithms are used to extract data from a data set. Primarily, we can divide classification into two categories. The first one being generative, and the second one is discriminative. So for generative, it tries to learn the model which creates the data through estimation of distributions and assumptions of the model. It is a prominent generative algorithm. A prominent generative algorithm is a naive Bayes classifier, or the Bayesian classification. You can use generative algorithms to predict unseen data. A generative classification algorithm models the distribution of individual classes. For discriminative, is a rudimentary classification algorithm that determines a class for a row of data. Logistic regression is an excellent type of discriminative classifiers. It also models by using the observed data and depends on the data quality instead of its distributions. Classifiers in machine learning. So classification is a highly popular aspect of data mining. As a result, machine learning has many classifiers. So here are a few: logistic regression, linear regression, decision trees, which we will discuss further later on, random forest, the naive Bayes or the Bayesian classification, which we will also discuss later today, the support vector machines, and the k-nearest neighbors, which is one of our topics today. For decision tree classification, it is a flowchart similar to a tree structure. So here you can see an example which resembles a tree. Every internal node refers to a test on a condition, and each branch stands for an outcome of the test, whether it is true or false. Every leaf node in the decision tree holds a class label. You can also split the data into different classes according to the decision tree. It will predict which classes a new data point would belong to according to the created tree. Its prediction boundaries are vertical and horizontal lines. The decision tree is the most robust classification technique in data mining. So since it's the most robust, we must see the strengths and weaknesses of decision tree. Strength for this is it's able to generate understandable rules. So it's very specific on that. It performs classification without requiring much computation. So it's really simple enough without needing to have a computation or an equation. It's also able to handle both continuous and categorical variables. It also provides a clear indication of which fields are most important for prediction or classification. For the weaknesses, one weakness is it's less appropriate for estimation tasks, where the goal is to predict the value of a continuous attribute. Another is it's prone to errors in classification problems with many class and relatively small number of training examples. It can be computationally expensive to train as well, so it's one of the weaknesses. The process of growing a decision tree is computationally expensive. Each node, each candidate splitting field must be sorted before its best split can be found. In some algorithms, combinations of fields are used, and a search must be made for optimal combining weights. Pruning algorithms can also be expensive, since many candidate subtrees must be formed and compared. The Bayesian classification, also known as the naive Bayes algorithm. This classifier assumes that the presence of one particular feature in a class doesn't affect the presence of another. Another assumption is this algorithm relies upon is that all features have equal importance. It also assumes that every feature is independent of each other and that all features contribute equally to the outcome. However, the naive Bayes classifier is notorious for being poor at estimation because it assumes all features are of equal importance, which is not true in most real-world scenarios or cases. The equation for Bayesian classification is here, as you can see, the Cx is equal to Pxc Pc over Px. So here, Pcx is the posterior probability according to the predictor x for the class C. Pc is a posterior probability of the class, hence Pc. Px is the prior probability of the predictor, hence Px. And Pxc is a probability of the predictor for the particular class. Apart from considering the independence of every feature, naive Bayes also assumes that they contribute equally. And to fully understand Bayesian classification, it must be on a different whole different presentation and discussion because it's going to be too lengthy if we include it here. So the next one is the nearest neighbor classification. This algorithm has a nonlinear prediction boundaries. As it's a nonlinear classifier, you would select the nearest neighbors of a test data point by using the Euclidean distance. You would have to count the number of data points present in different categories. KNN predicts the class of a new test data point by finding its nearest neighbor's class. So, and you would assign the new data point to the category with the most neighbors. So for the Euclidean distance, the formula is here. So d is equal to square root of x22 minus x11 raised to the power of 2 plus y22 minus y11 raised to the power of 2, where x11 and y11 are coordinates of one point or point A, and x22 and y22 are the coordinates of the other point or point B. D is the distance between x11, y11, and x22, y22 are points A and points B. We mostly use this distance measurement technique to find the distance between consecutive points. It is generally used to find the distance between two real-valued vectors. Euclidean distance is used when we have to calculate the distance of real values like integers or floats, etc. One issue with distance measurement technique is that we have to normalize or standardize the data into a balanced scale, otherwise the outcome will not be preferable. Balanced scale meaning they have to have the same units or type of measurements. So that's for Euclidean distance and with nearest neighbor classifications. So that's the end of the presentation for today. Thank you very much for listening in, and I bid you all a good night. Thank you.
So as what our presenter mentioned or related to his topic, no, this most commonly, no, actually we could able to use naman bias excels, no. The naive bias is linear classifier, no, while KNN is not, no. So it tends to be faster when applied to big data. No, since we are discussing about the big data, no, and because of course in comparison or even let's say in comparison, KNN is usually slower to large amount of data because of the calculations required for each new step in the process. So if speed is important, choose naive bias over KNN. Okay, again, so if speed is important in your research or in your proving, no, choose naive bias, no, over KNN. So in general, naive bias is highly accurate when applied to big data. So don't discount KNN, no, when it comes to accuracy true, no, as the value of K and KNN increases, the error rates decreases until it reaches that of the ideal bias for K infinity. So of course, decision tree, we have also decision trees Excel, no? And one of the three methods decision trees are the easiest to explain and understand. So most people understand hierarchical trees, and the availability of clear diagram can help you to communicate your results. So conversely, the underlying mathematical behind bias theorem can be very challenging to understand for the layperson. So KNN meets somewhere in the middle because theoretically, you could reduce the KNN process to an intuitive graphic, even if the underlying mechanism is probably beyond a layperson's level of understanding. Again, decision trees have easy to use features to identify the most significant dimensions, handling missing values, and deal with outliers. So although overfitting is a major problem with decision trees, the issue could, at least in theory, be avoided by using boosted trees at random forest. No, in many situations, boosting of random forest can result in trees outperforming either Bayes or KNN. And the downside to those add-ons are that they add a layer of complexity to the task and detract from the major advantages of the method, which is simplicity. So more branches on a tree lead to more of chance of overfitting. Therefore, decision trees work best for a small number of classes. Let's say, for example, if there are certain image only result in 2 classes, proceed or do not proceed. No, so it means to say that using of course decision tree is better. No, unlike Bayes and KNN, decision trees can work directly from table of data without any prior design work. If you don't know your classifiers, a decision tree will choose those classifiers for you from a data table, and the Bayes requires you to know your classifiers in advance. Okay, so again, as what our presenter discussed earlier, decision trees are very flexible, no, easy to understand and easy to debug. They will work with classification problems and regression problems. So if you are trying to predict a categorical value like red, green, up, down, or if you are trying to predict a continuous value like 2.9, 3.4, and others, decision trees will handle both problems. Probably one of the coolest things about decision tree is they only need a table of data, and they will build a classifier directly from the data without needing any upfront design work to take place. So to some degree, properties that don't matter won't be chosen as splits and will get eventually prone to so it's very tolerant of nonsense. Now to start it, set it, and forget it. Now, however, the downside, simple decision trees tend to overfit the training data more, so that other techniques, which means you generally have to do tree pruning and tune the pruning procedure. So you didn't have any upfront design cost, but you'll pay that back on tuning the tree's performance. Also, simple decision trees divide the data into squares. So building cluster around things means it has to split a lot to encompass cluster of data, because splitting a lot leads to complex trees, and risk probability are you are overfitting. Or let's say tall trees now get prone back, so while you can build a cluster around some feature in the data, it might not survive the pruning process. So there are other techniques like surrogate splits, which let you split along several variables at once, creating split in the space of the array, either horizontal and perpendicular, or either zero less than slope, in our calculus, or less than infinity. Cool, but your trees start to become harder to understand. And in your data structure and algorithm, it's complex to implement this algorithm. Other technique like boosting and random forest decision trees can perform quite well, and some feel these techniques are essential to get the best performance out of decision trees. Again, this adds more things to understand and use to tune the tree, and hence more things to implement. In the end, and more we add to algorithm, the taller the barrier to using it. For the naive bias, actually, I really wanted to differentiate the tree, So naive bias, requires you to build classification by hand, So there's not way to just toss a bunch of tabular data and have it pick the best features. It will use to classify, Picking which features matter is up to you. Decision trees will pick the best features for you from tabular data. If there were a way for naive bias to pick features, you're getting close to using the same techniques that make decision trees work like that. So give this fact, that means you may need to combine naive bias with other statistical techniques to help guide toward what features best classify, and that could be using decision trees. Naive bias will answer as a continuous classifier. There were techniques to adapt it to categorical predictions. However, they will answer in terms of probabilities, like let's say A is 90%, B is 5%, C is 2.5%, D is 2.5%. Now, Bayes can perform quite well, and it doesn't over fit nearly as much, so there is no need to prune or process the network. That makes them simpler algorithms to implement. However, they are harder to debug, no, and understand, because it's all probabilities getting multiplied by 1,000s of times. So you have to be careful to test doing what you expect, because naive Bayes does quite well when the training data doesn't contain all possibilities, so it can be very good with low amounts of data, because decision trees work better with lots of data compared to naive Bayes, no? So naive Bayes is used a lot in robotics and computer vision, and does quite well with those tasks. Decision trees perform very poorly in those situations. So if you're looking for the robotics and computer vision, naive Bayes is better, unlike the decision trees. Okay? If it, of course, teaching a decision tree to recognize poker hands by looking at millions of poker hands does very poorly, because royal flushes and goods occur so little, it often gets thrown out. So if it's thrown out of the resulting tree, it will misclassify those important hands. No, you just simply try to recall, no, your tall trees discussion from your data structuring algorithm. Now, just think if you are trying to diagnose cancer using this. Cancer doesn't occur in the population in large amounts, and it will get thrown out more likely. So good news is this can be handled by using weights. So we weight a winning hand or having cancer as higher than a losing hand or not having cancer, and that boosts it up the tree so it won't get thrown out. Again, this is the part of tuning the resulting tree to the situation that we discussed earlier. For decision trees are net because net, no, because they tell you what inputs are the best predictors or output of the open decision trees, can guide you to find it if there is a statistical relationship between a given input to the output and how strong that relationships, no, is, no. Open, the resulting decision tree is less important than relationship it describes. So decision trees can be used a research tool as you learn about your data, so you can build other classifiers. If you are dicing between using decision trees versus naive Bayes to solve a problem, oftentimes it's best to test each one better, no? You just try to test this using decision tree and try also to test using naive Bayes, no? Build a decision tree and build a naive Bayes classifiers, then have a shootout using the training and validation data you have. Whichever performs best will more likely perform better in the field. And it's always a good idea to cast each of those against k-nearest neighbor. Yung ibig sabihin po ng KNN, k-nearest neighbor. Predictors, because k-nearest has been shown to outperform both of them in some situation, and the k-nearest neighbor is a simple algorithm to implement and use. Again, if the k-nearest neighbor performs better than the other two, go with it. Okay, so I think that's it for this topic.